Interaction of energy with the atmosphere. Once electromagnetic radiation is generated, it is first propagated through the vacuum almost at the speed of light in the vacuum, and then through the Earth's atmosphere. Electromagnetic radiation passes through the vacuum without having any interaction or modification. However, while passing through the Earth's atmosphere, four different types of interactions take place. They are absorption, scattering, refraction, and reflection. Now, let us discuss them one by one. First, the absorption. Absorption is the process by which radiant energy is absorbed and converted into other forms of energy. The absorption of the incident radiant energy may take place in the atmosphere and also on the terrain. And absorption band is a range of wavelengths or frequencies in the electromagnetic spectrum within which radiant energy is absorbed by the substances present in the atmosphere. The cumulative effect of the absorption by the various constituents can cause the atmosphere to close down completely in certain regions of the electromagnetic spectrum. This is not desired for remote sensing, as no energy is available to be sensed. Ozone layer, we have the carbon dioxide within the atmosphere, and also we have the water vapor. These three are main atmospheric constituents that absorb the radiation. Ozone layer serves to absorb the harmful to the most living things, the ultraviolet radiation from the sun. Without this protective layer in the atmosphere, our skin would burn when exposed to the sunlight. Carbon dioxide is referred to as greenhouse gas, and this is because it tends to absorb radiation strongly in the far infrared or in the thermal infrared portion of the electromagnetic spectrum. And water vapor in the atmosphere absorbs much of the incoming longer wavelengths like thermal infrared and shortwave microwave radiation. The presence of water vapor in the lower atmosphere varies greatly from location to location and at different times of the year. For example, the air mass above a desert would have very little water vapor to absorb the energy, while the tropic regions would have high concentration of water vapor because of high humidity. The atmospheric gases absorb electromagnetic energy in different specific regions of the spectrum. They influence where they can look for remote sensing processes. Those areas of the spectrum which are not severely influenced by the atmospheric absorption and thus are useful to remote sensing sensors are called atmospheric windows. And in this figure, this gray area is representing the atmospheric blockage, and the white one is representing the atmospheric window. The x-axis is representing the wavelength, and the y-axis is representing atmospheric transmissivity, how much energy is being transmitted through the atmosphere, that has been plotted in this graph. And uh, mm, uh, all spectral regions are affected to some extent by absorption in the atmosphere, but some regions are less affected, and these regions are nearly transparent, uh, and some regions are completely blocked, and the open regions, I mean, where the atmospheric transmission is possible, the energy transmission is not highly affected, these regions are called atmospheric windows and are useful in remote sensing. As in this generalized diagram, it is showing the relative atmospheric radiation transmission of different wavelengths. Gray zones marked in this figure show the minimal passage of incoming or outgoing radiation, whereas the white denote the atmospheric window, in which the radiation does not interact much with the air molecules, and hence it is not absorbed. Most remote sensing instruments on air or on space platforms operate in one or more of these windows by making their measurements with detectors tuned to specific frequencies that pass through the atmosphere. However, some sensors, especially those on meteorological satellites, directly measure absorption phenomena such as those associated with carbon dioxide and other gaseous molecules. The next one is scattering. Atmospheric scattering is basically unpredictable diffusion of radiation by particles in the atmosphere. It occurs when particles or large gaseous molecules present in the atmosphere interact with the electromagnetic radiation. How much scattering will take place, that depends on several factors, including the wavelength of the radiation and also the diameter of the particles or gaseous molecules, and the distance the radiation travels through the atmosphere, etc. The amount of scattering is inversely proportional to the fourth power of the wavelength of the radiation. That means for the longer wavelengths the scattering will be rather much lower, but for the shorter wavelengths the scattering will be higher. Scattering is responsible for the blue appearance of the sky, as we know. The shorter violet and blue wavelengths are more efficiently scattered than the longer green and red wavelengths. That is why most remote sensing systems avoid detecting and recording wavelengths in the ultraviolet and blue portions of the spectrum, because the scattering basically causes haze on the image, and it makes the image interpretation difficult. And since the scattering is unpredictable and the amount of scattering is unpredictable, therefore introducing a specific filter may not serve the purpose always. The next one is the refraction. Refraction means basically bending of light when it passes through one medium to another medium of different densities. Now, for example, here we have a medium of less density, then we have another medium of more dense, and another medium then we have having less density. Now, when the light is being thrown, virtually it should go in a straight line, as we know that light travels at a straight line, but because of the change in the density of the medium, it will be deviated, and definitely this will cause a problem. Now again, as you can see, it is again bending. The speed of light in a substance can never reach the speed of light in the vacuum. Therefore, its index of refraction must always be greater than 1. For example, the index of refraction for atmosphere is 1.0002926. Refraction can be described by Snell's law, and in which we can see that the incidence angle is the theta 1 and the exitance angle is theta 2, and n1 is the index of refraction in medium 1 and n2 is the index of refraction in medium 2. So the formula is like this: n1 sin theta 1 is equal to n2 sin theta 2. Now, what is the relationship of refraction with the remote sensing? Serious errors in location due to refraction can occur in images formed from energy detected at high altitude or at acute angle. However, this location errors are predictable by Snell's law and can be reduced if one knows the index of refraction of medium 1 and medium 2 and the angle of incidence of the energy to medium 1. Then it is possible to predict the amount of refraction that will take place in medium 2. Now, within the atmosphere there is a continuous movement of air. The effect produced by the movement of masses of air with different refractive indexes, and this is called atmospheric shimmer. The effect of shimmer can be most easily detected in the twinkling stars. Shimmer results in blurring of the remote sensing images. Because of the atmospheric shimmer, the images will become blurred, and as we have learned that Snell's law can be used to detect and correct the atmospheric refraction, but since the atmospheric condition is not constant, or the index of refraction in different atmospheric layers also are not constant, therefore removing the effect of the atmospheric refraction is rather impossible, and as a result we may have blurred images. Next is the reflection. Reflection is the process whereby radiation bounces off an object like the top of a cloud or the terrestrial earth surface. However, here we are discussing the atmospheric reflection, not the reflection on the terrain. The reflection differs from the scattering in the way that the direction of reflection is predictable, whereas in case of scattering it is unpredictable, I mean in which direction the energy will be directed. A considerable amount of incident radiant flux from the sun is reflected from the top of the clouds or other materials present in the atmosphere. This results in recording of some extra amount of energy by the sensor in addition to the reflected energy from the terrain or in addition to the reflected energy from the target. Blurred images and appearance of clouds on the imagery are the main problems associated with the atmospheric interaction. Now, we have discussed all these 4 different types of interactions in the atmosphere, and we have also learned what are the problems we may face because of these interactions in the atmosphere. Now, after interaction in the atmosphere, the energy will hit the target, and then also different types of interactions will take place. In the next session, we shall discuss the interactions of the energy at the terrain.